Hello everyone. Today we are going to discuss the module 5 of integrated circuits and applications. So coming to the module 5, in this module 5 we are going to discuss the AC analysis of dual input balanced output differential amplifier configuration. In the last module we discussed the DC analysis of the various differential amplifier configurations. Now let us discuss the AC analysis. So in order to perform the AC analysis of dual input balanced output configuration, first of all, we have taken the uh, dual input balanced output differential amplifier. We know that the differential amplifier can be constructed by using two identical CE amplifier configurations coupled via the emitter resistor RE. So because here we have two inputs, you can see two inputs here. One is V1 applied to the base of Q1 and V2 applied to the base of Q2. And another thing is, here we are going to perform the AC analysis. So in order to perform the AC analysis, we need to calculate the voltage gain of the differential amplifier. Similarly, the equivalent input resistance at both the transistors Q1 and Q2 and the output resistance of both the transistors Q1 and Q2. So output is calculated at the collector terminal and input is applied at the base terminals of both the transistors. So that's why it is CE configuration. And to perform AC analysis, we are going to calculate the differential voltage gain, equivalent input resistance at both the transistors and equivalent output resistance at both the transistors. And our differential amplifier cannot be able to evaluate the current gain because of its high input impedance, it doesn't allow the flow of current through the system. So that's why this differential amplifier is not useful for or not preferred for current amplification. So it provides a sufficient amount of voltage gain. That's why we are going to calculate the differential voltage gain, not the current gain. So coming to the assumptions, here we are taking, because we are evaluating the AC analysis, we are going to take the DC voltages to zero potential. So both the DC voltages plus VCC and minus VE are set at zero potential. That is the first assumption. And second assumption is replace the transistor model into some hybrid model or R parameter model for analysis, for AC analysis. But here H parameter model is somewhat complicated. So we are moving to R parameter model for AC analysis. So in the R parameter model, we are including the AC emitter resistance small RE1 and small RE2. Those are the AC emitter resistors of Q1 and Q2 transistors respectively. So in order to let us move on to the some of the assumptions. Because the two transistors are identical to each other, that's from the definition of differential amplifier or from the construction of differential amplifier, IE1 is also equal to IE2, where IE1 is the amount of current flowing through emitter of Q1 and IE2 is the current flowing through emitter of Q2. So for this resistance, the AC emitter resistance of both the transistors Q1 and Q2 are also identical. So that's why we have replaced RE1 equal to RE2. Instead of RE1 and RE2, we have replaced it as small RE because both are identical. And similarly, the voltage across each collector resistance is shown 180 degrees with respect to the input voltages, because CE amplifier is also provides the phase inversion to the input. So at the output is 180 degrees out of phase with the input. That is the purpose of common emitter amplifier. So that's why you can see 180 degrees out of phase with respect to the input. So output is 180 degrees out of phase with respect to the input. Now let us move to the calculation of differential voltage gain, that is V0 by VID, where V suffix ID represents the differential input. Here you can see the R parameter, equivalent R parameter model for the dual input balanced output differential amplifier configuration. And the output is taken across the balance, that is the balanced output. So it is taken across the collector ends. So it can be VC1 minus VC2 or VC2 minus VC1. Here I have assumed VC2 at higher potential compared to VC1. So that's why the output voltage is VC2 minus VC1, where VC2 is minus RC into IE2 or IC2. Similarly, VC1 is minus IC1 into RC. So this is the negative sign is due to the current flow. The current flow is in this direction because we have grounded the DC voltages. So the DC voltages plus VCC and minus VE are set at ground potential. So that's why collector end is connected to the ground. And here also collector end is connected to ground, and emitter resistor RE is connected to ground. So V0 will be VC2 minus VC1, where VC1 and VC2 we have replaced it as minus RC into IC2 and minus RC into IC1. So then take RC as common. Here you can see IC1 minus IC2. Because the base current is like very less when compared to the collector or emitter ends, IC1 is approximated to IE1 and IC2 is approximated to IE2. Therefore, V0 is equal to RC into IE1 minus IE2. Now, in order to calculate the voltage gain or output voltage, we have to calculate the IE1 and IE2. So, in order to calculate the currents IE1 and IE2, where IE1 is the current flowing through emitter loop of Q1 transistor and IE2 is the current flowing through the emitter of Q2 transistor. So let us take the KVL for first loop. So it is minus V in 1 plus R in 1 into IB1 plus small re into IE1 plus capital RE into the amount of current flowing through capital RE is small IE1 plus small IE2. So plus capital RE into IE1 plus IE2 is equal to 0. Just upon rearranging, we will get the equation 1, that is V in 1 minus R in 1 IB1 minus small re into IE1 minus capital RE into IE1 plus IE2 is equal to 0. So second equation is minus V into plus R2 into IB2 plus small re into IE2 plus capital RE into that is IE1 plus IE2 is equal to 0. So again, by rearranging, we obtained the two expressions which is shown here. And in this expression, you can see we need IE1. The only extra amount of current is IB1. So again, IB1 please replace in terms of IE1. We know that the current gain beta of CE amplifier is defined as IE1 by IB1. So we can replace IB1 as IE1 by beta. Just we substituted IB1 as IE1 by beta suffix AC. Similarly, IB2 as IE2 by beta AC, where beta suffix AC represents the current gain of CE amplifier under AC analysis. So upon substitution here, you can see one thing. This is Rn1 by beta. Beta value is a higher value, and if you take IE1 as common here, if you take IE1 as common, it will be small re plus capital Re plus Rn by 1 by beta AC you will get. But Rn1 by beta AC is very less value. So we are going to neglect Rn1 by beta AC and Rn2 by beta AC because denominator is higher value. Beta AC is high. And Rn1 is very less compared to capital Re. Neglecting Rn1 by beta AC, you will get Vn1 as small re plus capital Re into IE1 plus capital Re into IE2. Similarly, we obtained V2 as capital Re into IE1 plus small re plus capital R into IE2. So here we have two unknowns and two equations are there. So IE1 and IE2 we are going to calculate. So that we are going to simplify and evaluate IE1 and IE2 by using Cramer's rule. From the Cramer's rule, IE1 can be defined as like a ratio consisting of numerator term as the overall constants of the expression, that is V1 and V2, followed by the second column elements will be the coefficients of IE2. For example, if you are calculating IE1, we have to consider the coefficients of IE2 in the numerator. And in the denominator, just to take the coefficients of IE1 and IE2. That is small re plus capital RE and capital RE in the first column. And second column, you have capital RE and small re plus capital RE. So that is our IE1. In order to simplify the numerator, this is in the form of a matrix. So calculate the magnitude of the matrix. That is by using AD minus BC. So that is V1 into RE, small re plus capital RE minus V2 into capital RE divided by small re plus capital RE into same small re plus capital RE, that is whole square, minus capital RE whole square. So like that we update the expression for IE1 and similarly we will calculate the expression for IE2. Just to substitute the values of IE1 and IE2 in the expression of V0 taken in equation 1. V0 is capital RC into IE1 minus IE2. Upon simplification, some terms gets cancelled and capital RC into we obtained as small re plus 2 capital RE into V1 minus V2. This is our differential input divided by small re into small re plus 2 capital RE. But remember that small re small re plus 2 into capital RE. Here we are neglecting 2 RE when compared to small re. So neglecting that, we will get V0 is equal to capital RC by small re into V1 minus V2. Or else we can see that a differential gain is equal to V0 by VID, which is equal to capital RC by small re. So here small re plus 2 capital RE gets cancelled. Same term we have, so both that's cancelled and you will get only small RC by small re into V1 minus V2. So finally we obtain the differential voltage gain as V0 by VID, which is equal to RC by RE. This is our differential voltage gain for dual input balanced output differential amplifier. And the second parameter that we need to calculate under AC analysis is equivalent input resistance. That is RI1. This RI1 is the equivalent input resistance for Q1 transistor, considering the input of Q2 transistor as 0 volts. So RI1 is equal to V1 divided by the amount of current flowing through this is IB1. So V1 by IB1 with V2 equal to 0 volts. But again replace IB1 as IE1 by beta AC. So you will get V1 by IE1 by beta AC. Because IC or IE is equal to beta IB. And we know the expression for IE1 by using Cramer's rule. We calculated the expression for IE1 and just substitute the value of IE1. So upon substituting, we obtained the term as beta AC small re into small re plus 2 capital RE divided by small re plus capital RE. Here remember that capital RE is very high when compared to small re. Small re is AC emitter resistance and capital RE is emitter bypass resistor. So this or you can say it as a parallel combination of RE1 and RE2 because this is emitter coupled resistor. which is the parallel combination of emitter resistance of Q1 and emitter resistance of Q2. So neglecting small Re, we will get the numerator, we will get 2 Re, and the denominator we will get capital Re. So this capital Re gets cancelled, and you will get Ri1 as beta AC 2 into beta AC into small Re. So that is our differential input resistance. Similarly, for calculation of input resistance at the for Q2 transistor, it is V into by IB2. Take for second input, other source input as 0. So V1 is equal to 0. So again replace IB2 as IE2 by beta AC with V1 is equal to 0. So please replace in terms of IE2 and beta, and from Cramer's rule we already obtained the emitter current expression. So substitute IE2 and neglect small Re in the denominator and numerator, and we have 2 capital Re and capital Re in the denominator. So capital Re in the denominator and numerator gets cancelled, and you will get Ri2 as same as Ri1, which is equal to 2 into beta AC into Re. And the output resistance R01 is nothing but the collector resistance. So R01 and R02 is equal to Rc. So from this session, we learned the AC analysis of dual input balanced output differential amplifier configuration. In the AC analysis, we calculated the differential voltage gain equal to A suffix D is equal to how much we obtained? It is equal to, you can say again, I am taking you back. It is Rc by small Re. Capital Rc by small Re. And the differential input resistance we obtained as 2 beta AC Re. Here you can see Ri2 is 2 beta AC Re. Similarly, Ri1 is also equal to 2 beta AC Re. And R2 is directly equal to Rc. So here finally we calculated the AC analysis of dual input balanced output differential configuration. Thank you for listening.